This is the screencast for section 9.1, example 3. Alright, so let's look over a few things. First of all, an infinite series in general, we've already defined. And then if it converges, the limit as k approaches infinity of a sub k equals 0. In other words, the tail end of this will approach 0, as we saw in the previous example. Each term gets closer and closer and closer to 0. Now we'll actually show that that concept relates to converging in exercise 62, but for now, know that it happens, and that means that if the limit as k approaches infinity of each term does not equal 0, then the series is going to diverge. Now again, we have this geometric series where each term is obtained from its preceding term by multiplying by the same number r. Now that's a specific type of power series that we're reviewing right now, and then we're going to go into more general power series in a little bit. Example 2 was a geometric series. Example 2, each term got multiplied by another 1/10. 3 was always there, but that denominator changed by a new multiple of 10, so 1/10 was the r value here. In the now try problem, each term got multiplied by 1/2, so the r value was 1/2. So another way of expressing that geometric series would be by taking the main coefficient, so in example 2 that was the 3, and multiplying it by a new r every time. So ar to the 0, r to the first, r squared, r cubed, etc. And eventually getting the sum of all of those terms put together. Now that's going to converge, if you remember from pre-calc, to a, the first term, divided by 1 minus the r value if the absolute value of r is less than 1. It's going to diverge if it's greater than or equal to 1. Now what that means is converging when the absolute value of r is less than 1 means that r itself has to be between -1 and +1, and that's for a geometric series, and we call that the interval of convergence. So the interval of convergence is the values for which the series will converge, and for this geometric series that's going to be between -1 and 1. So example 3, analyzing geometric series. Tell whether each series converges or diverges. If it converges, give its sum. So part A, we have the sum as n equals 1 to infinity of each of these terms. So we would do 3 times 1/2 to the 1 minus 1, 3 times 1/2 to the 2 minus 1, plus 3 times 1/2 to the 3 minus 1, plus 3 times 1/2 to the 4 minus 1, all the way to infinity. So we're adding all these up, the sum of each of these terms starting with n equals 1. Well, we recognize this as being a geometric series. The r value in this case is 1/2. Every time you're getting multiplied by 1/2. And 1/2 is in the interval of convergence. That's between -1 and 1. So I know that this series is going to converge. It's going to converge to what that formula was, the coefficient of the first term. So if we plugged in 1, 1/2 to the 1 minus 1, 1/2 to the 0 is 1. So we're left with 3. 3 is in the numerator over 1 minus the r value, which would then be 6. So this series, if I added up infinitely many terms, is going to converge to 6. Part B, we also recognize as a geometric series. The r value, each term, is getting multiplied not by 1/2, but actually by -1/2. And that is still in the interval of convergence. That's between -1 and 1. So this series is going to converge to 1, the leading term, over 1 minus the r value, so really 1 plus 1/2, which means that's going to be 2/3. So if I took each of these and kept adding and subtracting and adding and subtracting and adding and subtracting infinitely long, it's going to converge to 2/3, or 0.6 repeating. Part C, we've got another summation notation here, starting out with k equals 0 this time, to infinity of 3/5 to the k. Again, this is a geometric series. Each term is going to get multiplied by a new 3/5. So r is 3/5, and that is in the interval of convergence. That's between -1 and 1. So the series is going to converge to 1, because if we plug in 0, 3/5 to the 0, our first term is 1, over 1 minus the r value, 3/5, which then would be 5/2. So again, if I add all these terms all the way up to infinity, starting with k equals 0, then k equals 1, 2, 3, etc., I would converge to 5/2. Part D, we've got pi over 2 plus pi squared over 4 plus pi cubed over 8. Again, this is a geometric series. The r value, the new thing getting multiplied by each term, looks to be pi over 2. Now, pi over 2 is not in the interval of convergence, so 3 point something divided by 2 is going to be greater than 1. Therefore, this series is going to diverge. We can't tell what it's going to sum up to. It's going to diverge. The now try problem number 11 says tell whether the series converges or diverges. If it converges, give its sum. Well, we have 1 plus 2/3 plus 2/3 squared plus 2/3 cubed, etc. So really we have 2/3 to the 0 in this first term. That's fine. This is still a geometric series. Each term is getting multiplied by the same constant. That constant, or the r value, is 2/3, and that is in the interval of convergence. That's between -1 and 1 for a geometric series. Therefore, the series is going to converge to the leading term, 1, over 1 minus the r value, so that would be 3. So if I add up all these terms infinitely long, that value will approach 3. The other now try problem, number 19, is in summation notation. We're going to start out with n equals 1 and then go to infinity. So the first term would be e over pi to the first, then plus e over pi squared, plus e over pi cubed, etc. Well, each time we're getting a new multiplier of e over pi. So that is a geometric series. It's getting multiplied by the same thing every time each term is. And e over pi, which is about 0.865, is in the interval of convergence. It's just under 1. Therefore, the series is going to converge to, okay, that first term, so if n equals 1, that first term is going to be e over pi. That's going to be over 1 minus the r value, which is also e over pi. So, let's try and work this out. First, I'm going to find a common denominator in the denominator. So I'm going to change 1 to pi over pi. Now I can combine those terms. So I have e over pi over pi minus e over pi. And then if I, instead of dividing two fractions, if I multiplied by the reciprocal, the two pi's would cancel out and I get e over pi minus e, which you could probably figure out what that value is with your calculator. So if I added up all of these terms infinitely long, starting out with n equals 1, the sum would approach e over pi minus e.